Welcome back all of you. In this lecture we'll discuss about the correlation for discrete time signals. As we did in the case of the continuous time signal, we looked at all the different types of correlation which are possible in case of discrete time signals as well. And then we'll move on to some of the questions based on the different system properties and the correlation. So first we'll look at the cross correlation of discrete time energy signal. So obviously we are dealing with cross correlation, so that is two signals have to be present. Let's suppose the two signals present, discrete time signals present are xn and yn, and these two are finite energy signals. So the corresponding cross correlation function Rxy m can be defined as where m is the shift or lag in time. Okay, it can be defined in the term of now summation n tending towards minus infinity to infinity x of n y conjugate n minus m, which can be alternatively written as summation x of n plus m y conjugate of n. And we already know the significance of this order xy, the order of the subscript xy. That means the signal x precedes signal y. Okay, and now if xn and yn are both real signals, xn and yn are supposed to be real signals, then corresponding or cross correlation function can be represented as summation xn into yn minus n. It can be alternatively written as x of n plus n y of n. This is the scenario when xn yn are real signals. And again, if you reverse this order of the subscript r by x, it becomes this signifies that the y signal precedes x. So the expression will now change to yn x of n minus m. Clearly, the y signal now precedes x because it is shifted towards right. Xn is shifted towards right by m, and can be alternatively written as yn plus n x of n. So if we analyze these two equations, we can easily conclude that Rxym is equal to Ryx minus of n. So this was the cross correlation for the discrete time energy signals. Similarly, we can have a look at the cross correlation of discrete time power signals. Cross correlation of discrete time power signals. So again, cross correlation means we are dealing with two signals x and y, and these two are power signals. So the expression, mathematical expression will remain same, but now we'll use the time average. So R xy m, the cross correlation function, can be represented as limit n tending towards infinity 1 upon 2n plus 1 summation n equal to minus n to capital N x of n y conjugate n minus n, and it can be alternatively written as limit n tending towards infinity 1 upon n plus 1 summation n x of n plus m into y conjugate n. So this is the scenario for the power signal, the cross correlation function of the power signal. And again, if x of n and y of n are real signals, then we can write down the cross correlation function as limit n tending towards infinity 1 upon n plus 1 summation minus n to n x of n into y of n minus n, and it can alternatively written as towards infinity 1 upon n plus 1 summation minus n to n x of n plus n and y of n. So this is the cross correlation function for real signals x and y and which are power signals. Moving on, we can study the autocorrelation sequence of discrete time signals. Autocorrelation sequence of discrete time signals. I hope you remember the concept of autocorrelation function. The autocorrelation means that we aim to find out the degree of similarity between the signal with itself, with the time shifted version of itself. Find out degree of similarity between signal and the time shifted version of the same signal. So we can represent this Rxx, it is represented by Rxxm, which can be written as mathematically as n minus summation from minus infinity x of n minus n, or we can alternatively write it as summation x of n plus n x of n. This is the case when x of n is a energy signal. Similarly, when x of n is a power signal, the autocorrelation function can be written as limit n tending towards infinity 1 upon n plus 1 limit tending towards infinity 1 upon plus 1 summation times n x of plus 2. So n. This is when x of n is a power signal. And this capital N is the period, because it's a power signal, so obviously it will be a periodic signal, and this capital N represents the period of the signal. Next, we'll look at the properties of cross correlation and autocorrelation function for discrete time signals. Properties of cross correlation function and autocorrelation function for discrete time signals. First one we have already seen is Rxym is equal to Ryx of minus n, that is reverse the order of the subscript. Second property, this gives you the relation of signal energy and signal power. Relation to signal energy and signal power. It says that Rxx0 is nothing but energy of the signal, and it is equivalent to look at the expression of this autocorrelation function. This is the expression. You substitute m as 0, it becomes summation x square n, which is nothing but the energy of the signal. And this is the square, when x of n is a energy signal. Similarly, when Rxx0 is equal to power of the signal and is equal to limit n tending towards infinity 1 upon 2n plus 1 summation from minus n to n n square n gives you the power of the signal, and this is when x of n is a power signal. These are the important properties of discrete time signals, properties of auto correlation function, cross correlation function for discrete time signals. Okay, so now let us practice some numerical questions based on the topics that we've done so far. First one is the impulse responses of discrete time LTI systems are given below. Determine if the systems are causal and or stable. Okay, so we need to check the causality and the stability of the different systems whose impulse responses are given as. First one is Hn equal to 1 by 5 raised to power n. This is 1 by 5. Second impulse response is H of n 0.8 raised to power n 2 of n plus 2. Third one is 1 by 2 raised to power n 4 minus n. Fourth one is Hn equal to 5 raised to power n 2 of minus n. Fifth one is Hn equal to minus 1 by 2 raised to power n plus 1.01 raised to power n 2 of n minus 1. For all these 5 systems whose impulse responses are given, we will comment on the causality and the stability of the system. Okay, let us begin with the first one. For the first one, Hn is given as 1 upon 5 raised to power n given. Okay, we will first check the causality of the system. For a system to be causal, h of n should be equal to 0 for n less than 0. This is the condition for causality, right? So we'll check whether this impulse response fulfills this condition or not. So we can say that this given h of n, if we expand it a bit, is equal to it is 1 by 5 multiplied by u of n. U of n exists after n for n greater than 0 only. So and it is 0 for n less than 0. So we can say this h of n is equal to 1 by 5 raised to power n for n greater than 0, greater than equal to 0 rather, and it is 0 for n less than 0. Okay. So we can clearly say that this h of n is 0 for n less than 0, hence it fulfills this condition and thus a causal system. Next, let us comment on the stability of the system. Next, we'll check the stability of the same system. To check the stability, we know the condition is the summation Hn should be less than infinity. This is the condition for stability, condition of impulse response for stability. So we'll check the same for the given impulse response. Hn is given as 1 by 5 raised to power n q of n. So we'll check the summation from minus infinity to infinity for this given impulse response. So this is equivalent to n 0 to infinity 1 by 5 raised to power n, and if we simplify it, it becomes 5 by 4. If you simplify this, we will get answer as 5 by 4, which is obviously less than infinity, and hence it is a stable system. This is basically an infinite GP, and if you find out its sum, which is for A upon 1 as R, the common ratio will be divided by 4 and less than infinity, hence it's a stable system. Moving on to the next part of the same question. H of n, the impulse response is given as 0.8 raised to power n, q of n plus 2. Now let us check it for causality and the stability. Let us first check it for causality. For causality, the condition is h of n should be 0 for n less than 0. Now let us analyze this expression. So we can say that this h of n is equal to 0.8 raised to power n for n greater than equal to minus 2. So it is a shifted unit step function. It is multiplied with a shifted unit step function, and it will be 0 otherwise. Or we can say n less than minus 2. Hence, we can say that this is a non-causal system. So this condition gets violated. It's a non-causal system. And similarly, let us check the stability of the system. For stability, the condition is the summation should be less than infinity. Okay, let's check the same. Summation 0.8 raised to power n of n plus 2, which can be written as n is equal to minus 2 to infinity 0.8 raised to power n. It is again an infinite GP, and its sum, if you simplify it, comes out to be 5, which is obviously less than infinity. Hence, it is a stable system. Stable system, but non-causal system. Moving on to the third part. The impulse response given is h of n equal to 1 by 2 raised to power n q of minus n. So clearly it is, let's say, if you look at it, h of n is equal to 0 for n greater than 0. It is reverse of what we would say is causal system. Such a system is known as anti-causal. And if we talk about the stability of the system, then we'll find the summation of it from minus infinity to infinity. We look at 2 raised to power n of minus n. Let us rearrange the limits according to this factor. Terms n is minus infinity to 0, 1 by 2 raised to power n. And to simplify it, it comes out to be infinity. Hence, a unstable system. The same way you can attempt the next two parts, part B and part E, and take up if you have any doubts in those parts in the next doubt session. And I'll also give you some other practice questions. It's the same kind of a question, but for continuous time LTI systems. The impulse responses are given as first one is as 4t to t minus 2. Second one is ht equal to t raised to power minus 6t q of 3 minus t. Third part is ht t raised to power minus 6 modulus of t. Last one is ht t times of t raised to power minus t qt. Four systems are given with the following impulse responses. Comment on the causality and stability of the systems. Okay, next question is, it's a very good kind of important question, very good number of notes. Find and sketch the autocorrelation function for xt. This is the given signal t raised to power minus 80 qt for a greater than 0 to to find and sketch the auto-progression function for this. Try to attempt this question as well, because you just have to substitute this xt to the expression of auto-progression function, which is rx tau, and then for different values of tau, that is for tau and 0 and tau and 0, try to analyze the final expression of rx tau and try to plot it. If you have any doubts, we will take up in the next doubt session. That is all for this lecture. Thank you.